So what we want to look at today is called the chain rule. Like I said, I used to call this, I think of the chain rule as the cabbage rule. And I like the idea of the cabbage rule because think of a cabbage as it has layers, right? And if you've ever tried to cut up a cabbage or do something with a cabbage, to get to the inside, you got to like peel back the layers from the outside. So it's this idea of layers. And then a few years ago, as I was doing this, and I was calling it the cabbage rule, somebody said, this is kind of like Shrek, right? Because Shrek has layers like an onion, the same. So all of those ideas of something with layers that you can peel back outer layers to get to the inside. So that's our idea here. So whether the official name of this is the chain rule. So whether or not you want to think about it as the cabbage rule or the Shrek rule or the onion rule or whatever, it's that idea of layers. So I want to get that in your head. So when we think of functions, one of the things we talked about with functions was the composition of functions, which is how to combine two functions, how to put one function inside of another. So if we remember that, if I have two functions, f and g, and I want to find f of g of 2. We looked at this at the beginning of this year when we reviewed in calculus, and then you did this from pre-calc also. We would find what is f of g of 2. So you'd put 2 into g and get 2 squared is 4 is 7. Then we find f of 7, which is the square root of 8. Or we'd look at this as a function and say, well, what is f of g? This is how this is going to connect with what we're doing today. We're going to put the whole function inside for x, and we get x squared plus 3 plus 1. And we get x squared plus 4. Now, we know we cannot simplify that and take the square root of both of those. But you can see from up here, when we had a 2 in here, if you put a 2 into there, you get the square root of 8. The same thing we got before. Now, what's going to be more important for us, this is what we've done before. This is all the stuff we did before with this. What's going to be more important for us now is not combining functions, but actually taking functions apart. So if we want to find f of g of x, so another way to think about that is f of g of x. G is the inside, f is the outside. So if we have our original function of 2x, 2 times the quantity x minus 1 cubed, what is our inside function? What's the inside part? X minus 1. And then what would the outside part be? 2x cubed. So let's pause there for a second. So you can see what we're going to, as we talk about this chain rule, this Shrek rule, we're going to talk about there being an inside part and an outside part. And that's going to be really important, is that we can take apart the layers of the function in order to take the derivative. So what we're looking at is how to take the derivative of something like this. So that is our chain rule. So now, before we get to there, let's take it up a notch. Let's say we have this function, the sine cubed of e to the x. Now, first off, when we see a cube right here in sine, it may help you to think about it. We write it there, but really it means a cube out like that. So that means the same thing. But we will write it like this. But you may want to visualize it like the right. So we have f of g of h. So which function is the most inside function? Well, let me rephrase that. H is the most inside. F is the most outside. So you could look at this as two ways. You could look at it and say which function is the most inside one, which is the most inside layer, or which one is on the outside and the most outside layer. You can attack it from either way. Okay? Now, I have these. The G is not even on your paper there, it didn't show up. And these are not in the right order, so I apologize for that, not intentional. So let's start inside. H. What's the most inside part? E to the x. G is the next, which would be sine. And then all the way on the outside would be x cubed. Our goal in this section is to be able to take the derivative of that when we're done. Where you have these functions inside of functions. Okay? So, it's going to take us a little bit of time to build up to that, but that's what we're going to look at. So, cabbage rule, chain rule, Shrek rule. Here is the chain rule. So, the derivative of f of g of x is f prime of g of x times g prime. That's the formula. But just like the product rule and the quotient rule, we want to think about this in terms of words and we do it. What was the product rule? Who wants to do the product rule?
The derivative of the first times the second plus the first times the derivative of the second.
Perfect. Quotient?
Down d up minus up d down over down down.
Perfect, right? So those are the words we say in our head as we're finding those. So for chain rule, we're going to say this. Derivative of the outside with the inside staying the same times the derivative of the inside. So write that down and then we'll go through that. Derivative of the outside with the inside staying the same times the derivative of the inside. So you notice what we have here. F is our outside function. G is the inside. So we take the derivative of the outside. Inside stays the same. It's still g of x inside. And then we multiply by the derivative of g. So let's look at an example. Find the derivative of 2x cubed plus 3x quantity squared. So the first thing you want to think about is what's the outside part? X squared. So think, okay, x squared. How do we find the derivative of x squared? Bring down the 2, subtract 1, and end up with just x, right? So we'll do the same thing here. We bring down the 2, subtract 1 from our exponent. But our chain rule says it's derivative of the outside, but the inside stays the same. So the inside is exactly the same as before. Times the derivative of the inside. So now we go to the inside and we just take the derivative of that, 6x squared plus 3. And there is our derivative. At this point, we are not going to simplify it. We're just going to leave it like that. We're just trying to understand the rule. And so we want to be able to see the rule to kind of see how it worked out. Okay. Now, if we wanted to, I'm not going to do this. You can do this when you're bored later and have your extra free time. If you wanted to, you could multiply this out and FOIL this top part out as a polynomial. Take the derivative of it. Multiply this out, and you'd be able to see that they're exactly the same, right? You could do it two different ways with that. Now, you can't always do it that way, let's say we have this. What's the derivative of cosine x squared? Obviously, you can't multiply this one out, okay? But with our chain rule, derivative of the outside, inside staying the same. So what's our derivative of our outside? Cosine. And the derivative of cosine is? Negative sine. So it's negative sine, derivative of the outside, inside staying the same, times the derivative of the inside, which would be 2x. So just like product rule and quotient rule, I think the key to this one is having those words in your head. Derivative of the outside, inside stays the same, times derivative of the inside. And if you can think of that as you go, it's going to help. Okay? All right. Not sure what's going on over here. Oh, that's number 2. That's what's going on. Like that, maybe? All right. All right. Try these two. See if you can do these two. See if we can kind of understand how this works. Very good. Both of those. All right. So basic idea of the chain rule. Derivative of the outside, inside stays the same, times derivative of the inside. Okay? All right. Let's kind of kick it up a little bit here. Let's look at what's called the power chain rule. So when we're looking for like a general trend here. The general trend says this. Way to kind of think about it or break down. If you have something in parentheses raised to an n, and I just call whatever inside here junk. You got something. Some junk inside there. The derivative is just you bring down the n, you subtract by 1 from your exponent, and the junk just stays the same. Whatever it is. Then you multiply by the derivative of the junk. And the idea is that when you go back here and you look at this one, you can almost just, if you think of that part right there, you can almost ignore what it is. And you know you just bring down the 4, you subtract 1, that just stays the same. Don't make it harder by thinking about that, right? Just do it in steps. And okay, whatever all that junk in the parentheses, it doesn't matter. Bring down the 4, subtract 1, just write it down again. Then, once you do that, then go back to that and say, okay, what's the derivative? So as these get more complicated and they look uglier, so to speak, break it down into those chunks, right? And whatever's inside, don't even mess with it. Just leave it there. That's what I mean by junk. Whatever's there, don't worry about it. So let's look at an example. Tangent to the 4th of x. Now, I'm just going to say, okay, the derivative, bring down the 4, subtract 1, and I get to there. That is the derivative of the outside. Right? It may help if you want to think about this kind of like that. Bring down the 4, subtract 1. Times the derivative of the inside, which the inside here is tangent. Do we remember the derivative of the inside? What's the derivative of tangent? Do you remember that one? We've already done sine is cosine. Cosine's negative sine. Derivative secant squared. So the derivative of our tangent is secant squared. Let's consider e. The derivative of e to the x, as we know is just e to the x. So the way I refer to it, the term I use is the derivative of e to the junk is just e to the junk times derivative of the junk. So what is the derivative of e to the 3x squared plus 4x? The derivative of e to the junk is just e to the junk. So it's just e to whatever the same thing is. then times whatever the derivative of the junk is. So now as I go to take the derivative, I can forget about the e and just look at the exponent and get 6x plus 4. So really one of the keys to doing chain rule is to really think about breaking it up, and that's why, going all the way back to where we started today, breaking it up and thinking about the layers, right? This is the one reason I like the cabbage rule, maybe over Shrek rule, but same idea applies. If you think about the cabbage rule, in order to get to the inside, you got to like deal with and peel back the outside layers. So if you look here, you have to deal with the outside, the E part, and you deal with that, and your inside doesn't change. And then once you deal that, you can peel it back and not worry about it anymore, and then just go to the next layer inside and take the derivative. So it's like peel back the outside, take the derivative of the outside, inside doesn't change. Once you do that, you can stop, regroup. Okay, now let's just look at the inside part. Now let's just take the derivative of the inside. So you're working on it in layers, which makes these easier than seeing this some gigantic problem that you're trying to solve. Okay. All right, try these two. We'll try two more. See if you... There's a hint if you need it. The derivative of cosecant is negative cotangent cosecant. So you probably don't remember that one. That was one of those trig ones we said you don't need to remember. I'll give it to you when we need to use it. So. All right, so first one there is good. Bring down the 3, subtract 1. So that's 3 cosine squared times derivative of the inside, negative sign. So the next one, what's the outside one?
Cosecant.
Cosecant. So what is the derivative of cosecant? What I gave it to you down here, right? It's negative cotangent cosecant. But because of chain rule, what is chain rule? Derivative of the outside with the inside what? Stays the same. So my inside is still cosine. Times the derivative of the inside. And what is the derivative of the inside?
Negative sign.
Negative sign. And we're not going to do anything more with that at this point. So that looks crazy, and it's got trig functions inside of trig functions and all that kind of stuff. We're not going to do anything with it. We're just trying to, this is just helping us understand the patterns of what we're doing. So it looks really complicated, and it is. But just kind of take it step by step, peel back the layers, and just do the one thing at a time that you need to do. Questions on that, or does that kind of make sense? Make sense? Okay. All right. We want to look at one more today. And that is looking at some exponentials. So, let's see what you remember about logarithms a little bit. So, if I have log base 3 of 9, that's 3 to what power is 9? Be 2, right? So that would be then 3 squared, which is just 9. So this gets us to this general form that if I have e to the natural log of a, wouldn't the natural log be log base e? So it kind of fits the same pattern, and you can see up here, this is mathematically wrong, and what I'm about to say is not mathematically correct. But this 3 and the log 3 kind of cancel, and that's just your answer, right? That's not exactly what you're doing, but that's how it works out. So here that same works out, so this answer is just A. Does that make sense? All right. Now, if we combine that with another properties of logarithms, which says if we have a number in front of the logarithm, do you remember we can take it up as an exponent? So that I could write this as e to the natural log of a to the x. So then, this, just like up here, these canceling to get there, this can cancel and just give me a to the x. Okay. Now, this is something we will use a few times this year. And I call it, we have to E it, where we have to do this. So what this allows us to do is if, and at this point, this is not going to seem like you would want to do that. This is going to be helpful, but it actually is. So if I have x squared, and I say, well, we need to E it, that means we can write it as e to the natural log of x squared. You know, if you have cosine, and I say we need to E it, that would be e to the natural log of cosine. Now, that looks like it's making it much harder, but it actually helps us here in a second when we look at E-ing it to try to solve. So, what we want to do is we want to find the derivative of a to the x. Now, we know already what is the derivative of e to the x. E to the x. So the question is, now, let's say we have the derivative of not e, but let's say we have the derivative of 2 to the x. What would that be? So that's what we're trying to find. So our derivative of a to the x. And whether or not you want to write this down or not, I'm going to go through the proof to show you how we do this, where it comes from. So first thing we're going to do is we have to e it. So we're going to rewrite this as e to the natural log of a to the x. Our properties of logarithms say we can take this x and move it out front. So what we're really doing is we are taking the derivative of that. Now, from what we already talked about today, what is the derivative of e to some junk? It's just from the previous page, right? It's e to that junk times the derivative of the junk. Well, what's the derivative of that exponent? Isn't that just some number times x? So what's the derivative of 2x? 2. What's the derivative of negative 7x? Negative 7. So what's the derivative of natural log of a times x? Natural log of a. Now, this is really what we had here, which is what we had here, which is what we had here, which is really just a to the x. So our formula for what is the derivative of a to the x is just a to the x times the natural log of a. Now think about e to the x. This fits this pattern. So the answer would be the natural log of e times e to the x. But what is the natural log of e? E to what power is e? If we just take the natural log of e, that's just 1. So because of that, this natural log of e just goes away, and so the derivative of e is just e to the x. But if it's 2x, now my derivative of 2x is the natural log of 2 times 2x. You put this natural log of the base in front. The pattern holds for e, it's just that natural log of e is 1, so it goes away, so we don't need it. So let's say we have, what's the derivative of 3x squared plus x? What's the outside part? 3 to the x, which would be natural log of 3 times 3. The derivative of the outside, inside stayed the same, times derivative of the inside. Okay. All right, that's where we're going to stop today. That's our basic idea of chain rule. We're going to have another Delta Math homework here. Tomorrow, we're still going to go on with the chain rule tomorrow, but tomorrow we're going to look at, kind of give you a preview here, tomorrow we're going to look at repeated uses, where you have like 3 functions inside, or something like this, where you have to do chain rule, but you have to do product rule. So you do chain rule inside of, they get harder. Right? That's basically what we're going to look at tomorrow, okay?